Hi everyone, welcome to the Electrical Minds Hub. In today's session, we'll explore one of the most important and often misunderstood topic in electrical engineering, harmonics. By the end of this video, you'll clearly understand what harmonics are, why they occur, how they affect our system, and most importantly, how to identify and control them effectively. So let's get started. So, in an ideal AC electrical system, both voltage and current waveforms are perfect sine waves oscillating at a single frequency. For example, 50 Hz in India, 60 Hz in the US. But in real world system, we rarely see such perfect waves. Many of our modern electrical devices like variable frequency drives, rectifiers, inverters, computers and LED lights distort the waveform. This distortion introduces extra frequencies that are integer multiple of fundamental frequency and these multiples are called harmonics. In simple words, जब हमारे सिस्टम में साइन वेव परफेक्ट नहीं रहती है और उसके अंदर छोटे एक्स्ट्रा फ्रिक्वेंसीज मिक्स हो जाते हैं, उन्हें हम हार्मोनिक्स कहते हैं. As in the waveform shown here, resultant of all harmonics combined can be seen. These harmonics are responsible for heating, vibration and reduced system efficiency. So understanding them is extremely crucial for maintaining power quality. So let's define harmonics formally. Harmonics are voltage or current component whose frequencies are integer multiple of fundamental frequency. Now, why it is important to study harmonics? Because harmonics can lead to major problems. They cause additional losses in transformers, overheating in cables, false tripping of circuit breakers, and even malfunctioning of sensitive equipments. If you look at the images on the slide, the first shows a pure sine wave, smooth and clean. The second one shows a distorted wave. This is what happens when harmonics are present. You can see that even though the fundamental frequency is same, the waveform shape changes drastically. This is the visual proof of harmonic distortion. So now we will talk about classification of harmonics, meaning how many type of harmonics can be present in a system. So harmonics can be classified in several ways, mainly by their order, phase sequence and nature of frequency. So let's understand them one by one. First, based on order, harmonics are divided into even harmonics, odd harmonics, triplet and interharmonics. So first we will talk about odd harmonics. Harmonics such as 3rd, 5th, 7th, 9th, 11th and so on. These are the most common in our power system because most nonlinear loads like rectifiers, inverters generate symmetrical waveforms that naturally produced only odd harmonics. What are even harmonics? Harmonics like 2nd, 4th and 6th are very rare in our balanced system. Their presence usually indicates waveform asymmetry, faulty equipment or some abnormal operation. So if you see even harmonics in your reading, consider it a red flag. कुछ ना कुछ सिस्टम में फॉल्ट जरूर है. Next, we have a special category called triplet harmonics. These are harmonics whose order is a multiple of 3, such as 3rd, 9th and 15th. These are also called zero sequence harmonics because in a 3-phase system, all 3 phases of these harmonics are in phase with each other. They do not cancel out. Instead, they add up in the neutral conductor, which can cause neutral overloading and overheating. That's why triplet harmonics are particularly dangerous in a system with large single phase load like computer, network or LED lighting system. So now let's talk about interharmonics. Unlike regular harmonics which are integer multiple of fundamental frequency, interharmonics are integer multiples, for example 2.5, 3.8 times the fundamental. They are produced by equipment such as variable speed drives, cycloconverters, power converters with irregular switching frequencies. Interharmonics can cause light flicker, noise in communication line, and even vibration in motors. In short, odd harmonics are most common, even harmonics indicate issues, triplet harmonics overload the neutral, and interharmonics create instability and noise. So finally, based on phase sequence, harmonics can rotate in same, opposite or zero direction with respect to fundamental frequency. So based on phase sequence, harmonics can be divided into three: positive sequence harmonics, negative sequence harmonics, and zero sequence harmonics. So what are positive sequence harmonics? Harmonics like 4th, 7th, 10th, they rotate in same directions. So that's why they called positive sequence harmonics. So what are negative sequence harmonics? Harmonics like 15th, 11th, 17th rotate in opposite direction of fundamental frequency, causing torque, pulsations and heating in rotating machines. Zero sequence harmonics, harmonics like 3rd, 9th, 15th have no rotation and combined in the neutral path. So overall, harmonics classification help us predict their impact, whether it's a torque fluctuation, heating or neutral current overload, making it easier to plan suitable mitigation technique. So now we will talk about another important topic, cause of harmonics. So harmonics can originate from different sources like load generated harmonics and system generated harmonics. So when we talk about load generated harmonics, these occurs when non-linear devices draw current in pulses instead of smooth waves. Common examples include VFD, computer, UPS, LED drivers, welding machines, and chargers. These causes current waveforms distortions, which in turn distort the voltage. So next is system generated harmonics. These occurs due to interaction between system components like transformers, capacitors and inductors, even without non-linear loads. So resonance between these components can amplify existing harmonics. So harmonics can also be generated through converters and arc furnaces. So when we talk about converter generated harmonics, these comes from power electronic converters such as rectifiers, inverters and HVDC system. So they generate specific harmonics orders like 5th, 7th, 11th and 13th. Next is arc generated harmonics. These arise from unstable loads such as arc furnaces or discharge lamps, which produce random and high frequency harmonics, leading to flicker and electrical noise. In short, जहाँ भी वेवफॉर्म स्मूथ नहीं है वहाँ हार्मोनिक्स होते हैं. So now the question is, how can we identify the order of harmonics? Like हमें पता कैसे चलेगा सिस्टम में कौन से ऑर्डर का हार्मोनिक प्रेजेंट है. The harmonic order simply means how many times the frequency of that harmonics is greater than fundamental. The formula is H is equal to FH by F1. If the fundamental frequency is 50 Hz and component is found at 250 Hz, then 250 divided by 50 equals 5. So that's the fifth harmonics. For converter and drives, there is another formula, H is equal to N into P plus minus 1, where P is the pulse number of converter. For example, a 6 pulse converter harmonic appears at 5th, 7th, 11th and 13th. Hope you are getting this now. So now let's discuss total harmonic distortion, another important topic. So what is THD? THD means total harmonic distortion. It's a key parameter used to measure how much distortion is present in a waveform. In simple words, THD tells us how polluted our voltage or current waveform is with unwanted harmonics. Mathematically, as you can see in the formula also, THD is the square root of the sum of all harmonic voltage squared divided by the fundamental voltage. A low THD means your waveform is clean. A high THD means your waveform is distorted, which can cause overheating, misfiring and power quality problems. So THD act as a health indicator of your electrical system. जैसे हम ब्लड टेस्ट से हेल्थ चेक करते हैं ना, वैसे THD से सिस्टम की पावर क्वालिटी चेक होती है. So now let's talk about THD limit as per IEEE. First of all, what is IEEE 519? IEEE 519 is an international standards that tells us how much harmonic distortion is present or acceptable in an electrical system. In simple words, it gives us guidelines how to keep harmonics under control. This standards provides recommended limit for two things. Number one, voltage THD. Number two, current THD. So when we talk about voltage THD, also called THD-V, this is the allowable voltage distortion at the point of common coupling or PCC. Basically the point where your system connect to the utility. Number two, current THD, also called THDI, for all user connected to the utility. This tells us how much current distortions we are allowed to inject back into the grid. And overall the purpose of IEEE 519 is very simple: to maintain good power quality, ensure system reliability and protect equipment from damage caused by harmonics. So in short, IEEE 519 is the rule book for acceptable harmonic levels. So as you can see, this standard defines acceptable limit for voltage THD and current THD at the point of common coupling. That's the point where your system connects with the utility grid. According to IEEE 519, for voltage the THD should be less than 5% under normal condition. For current, THDI limits depend upon system size and short circuit ratio, typically around 8 to 12% for most industrial networks. The goal of this standard is very clear: to ensure stable power quality, reduce losses and protect equipment from the harmful effect of harmonics. If these limits are crossed, you can face issues like capacitor failure, overheating in transformers, malfunctions of relays, and even penalties from utilities in some cases. So in short, IEEE 519 एक ग्लोबल बेंचमार्क है जिसमें हम मेज़र करते हैं कि हमारा सिस्टम हार्मोनिक पॉल्यूशन के अंदर सेफ है या नहीं. Following it means your system is healthy, efficient and compliant. So now let's clearly differentiate between voltage THD and current THD, because both are important but represent different things. So voltage THD tells us how much voltage waveform is distorted. It depends on system impedance and harmonic current flowing through it. Even if your source voltage is clean, when harmonic current passes through a system impedance, small voltage distortion appear. That's why THD values are usually low, typically under 5% in well-designed system. However, when THD-V increases beyond its limit, you may face insulation stress, capacitor heating and malfunctioning of sensitive devices. So now we'll talk about current THD. This represents the distortion in the current waveforms drawn by nonlinear loads. Loads like rectifiers, variable frequency drives, computers and LED lights draw current in a short pulse instead of a smooth sine wave, as we have also discussed in previous slide, and this creates high THDI. Current distortion not only increases losses and heating but also indirectly distorts the voltage across other connected equipments. So on this slide we have a graph that shows how total harmonic distortion or THD changes when the duty cycle of a system varies. Along the horizontal axis you can see the duty cycle, and on the vertical axis we have a THD percentage. You will notice that there are multiple curves, each representing a different switching frequencies like 50 Hz, 100 Hz, 200 Hz and 1 kHz. Now what does this graph tells us? As the duty cycle increases from 0 to around 10 to 20%, the THD rises sharply. This means that at certain duty cycle the system generates very high harmonic distortion. After reaching the peak, all curves begin to fall as the duty cycle continues to increase. So beyond a point, increasing duty cycle actually reduces THD. Another important thing we can notice is that higher switching frequencies generally give lower THD, especially at a medium and high duty cycles. So that's why 1 kHz curve stays relatively lower compared to 50 Hz or 100 Hz curve. In simple terms, low duty cycle means THD increases quickly. Mid duty cycle means THD reaches maximum. High duty cycle means THD start reducing. Higher switching frequency means better THD performance. So this graph tells us understand that THD is not constant. It changes with the system's operating conditions, and choosing the right switching frequency can greatly improve our power quality. So now let's understand another related terms, TDD or total demand distortion. While THD measures distortion with respect to the instantaneous current, TDD measures its relative to maximum demand current. This makes TD a better indicator in systems where load varies throughout the day. For example, during light conditions, THD may appear high because the denominator fundamental current is small, but the TDD corrects it by comparing harmonic to the full load current. So TDD gives us a more realistic picture of harmonic distortion for compliance and design purpose. So now let's finally discuss how to eliminate or reduce harmonics. So when we talk about filtration or elimination of harmonics from the system, we talk about two types of filtration. One is path-based filtration, second is source-based filtration. So when we talk about path-based filtration, so in this approach we provide a separate low impedance path for harmonics current to flow, so they don't circulate through the main power lines or sensitive equipment. This is done by using various filters which can be either passive or active. So first is passive filters. So what are passive filters? These are the simplest and most widely used filters. A passive filter is made up of basic components, inductors, capacitors and sometimes resistors, tuned to a specific harmonic frequency. For example, if your system has dominant 5th and 7th harmonics, you can design LC filter tuned to those frequencies. These filters offer a very low impedance path at that harmonic frequency, so those harmonics get diverted and absorbed by filter instead of polluting the main system. Passive filters are low cost and reliable, but they have some limitations. They work best at fixed loads and cause resonance if not designed carefully. So they are ideal for stable systems like induction furnaces and constant speed drives. Next is active filters. So active filters are more advanced. They continuously sense the current waveforms, detect harmonic in real time, and inject an equal and opposite harmonic current into the system to cancel them out, just like active noise cancellation in the headphones. Active filter can handle multiple harmonics orders simultaneously and adapt to changing load condition. These are expensive but very effective for modern industries where load vary frequently, like data centers, manufacturing plant and commercial buildings. Next is hybrid filters. So what are hybrid filters? Some systems even use a combination of both, like where passive component handle low order harmonics and active handle higher or variable harmonics. So we use both in hybrid filters. This gives a perfect balance between performance and cost. So in short, path-based filtration means giving harmonics alternate route to flow instead of letting them disturb your main power system. So now let's talk about source-based mitigation or source-based filtration. Now let's look at the second approach, reducing harmonic at the source itself. Here, instead of filtering out the harmonics after they are generated, we modify the design or technology of the equipment so that it produces few harmonics in the first place. So the first is use of multi-pulse converters. Traditionally 6-pulse converter, which are used in most rectifiers and VFD, are major source of 5th and 7th harmonics. If we replace them with 12-pulse or 18-pulse converters, these harmonics shift to higher orders like 11th, 13th or beyond, which are much easier to filter and have less effect on our system. This technique is common in large DC drives, induction furnaces and heavy industrial system. So more pulses is equal to smoother waveform and lower harmonics. The next is active front end AFE drives. Modern variable frequency drive now comes with active front end or AFE rectifiers. These rectifiers draw almost sinusoidal current from the supply and automatically maintain near unity power factor. AFE drives continuously monitor and shape the input current to eliminate harmonics at the source level. Although they are costlier, they provide superior performance and are ideal for sensitive or high efficiency installation. And the next is phase shifting transformers. Another effective method is using phase shifting transformers. By supplying power through transformer with phase shifts like plus minus 15 degree or plus minus 13 degree, harmonic current from different load get phase cancelled. This technique is often used in systems with multiple rectifier or large parallel drives. And the last is power factor correction and design improvement. Sometimes harmonics can be reduced indirectly by improving system power factor and ensuring balanced loading. Proper cable sizing, grounding and separating sensitive circuit from non-linear loads also help minimizing harmonic propagation. Let's talk or quickly summarize the entire concept of harmonic mitigation. So first is path-based filtration, which removes harmonics after they are generated using filters. Second is source-based mitigation, reduced harmonic at the point of generation by using improved converter or drive designs. Passive filtration are cost-effective but static. Active filters are dynamic and intelligent. 12-pulse or AFE drive are the best solution for new industrial system aiming for IEEE 519 compliance. A well-designed mitigation plan ensures stable voltage, lower heating losses, higher equipment life and better overall system reliability. In short, हार्मोनिक को कंट्रोल करना एक बार का प्रोजेक्ट नहीं है, बल्कि एक कंटिन्यूअस मॉनिटरिंग और इम्प्रूवमेंट प्रोसेस है. So whether you are designing a plant, upgrading equipment or maintaining existing system, always analyze, measure and mitigate harmonics for better power quality and long-term performance. So finally, that brings us the end of today's session on harmonics, one of the most crucial topic in power quality and electrical engineering. We started with the basic of harmonics, learned how they are generated, how to identify them, how to measure them using THD and TDD, and finally explored practical mitigation technique. So both path-based and source-based. Remember, harmonic may be invisible, but their impact on your system's performance, efficiency, and reliability is very real. So always analyze, monitor, and control harmonics in your electrical network, because better power quality means better performance. If you found this explanation helpful, do take a moment to like this video, share it with your colleagues or friends, and subscribe to the Electrical Mind Hub for more such in-depth and easy to understand video on power quality, energy systems and electrical engineering concept. आपके एक लाइक और सब्सक्राइब से मिलती है हमें मोटिवेशन, ताकि हम और भी इंफॉर्मेटिव वीडियो आप तक ला सकें. Thanks for watching. I will see you in the next video. Till then, keep learning, stay safe and keep your power clean. Thank you.